Okay, so for those of you who haven't seen this show before, this is the Daily Space. We are a product of CosmoQuest.org, which invites you to help us map out our solar system and beyond. We actually are having a call for increased information on Mars and Mercury. So if you all could do me a favor, and if you're not using all your brain cells to watch this show, can you guys click over to CosmoQuest.org and help us by mapping out Mars and Mercury? Science is needed, and your help doing science is needed. Now, for today's top story. This is actually something of a follow-up from a presentation that we talked about yesterday. So yesterday I discussed how there are scientists trying to explain the composition of Pluto, and one of the ways they've come up with to do this is by modeling Pluto as a composite of a whole lot of comets. Well, today I have a similar story, but this time it's about Earth and Mars. Scientists who are working to understand exactly how things moved around in our early solar system are looking at what happened if Jupiter, during the early days of the solar system, migrated inwards towards the sun, and while in a 3:2 resonance with Saturn, which means that for every 3 times Jupiter went around the sun, Saturn went around twice. What if during this period of resonance, Jupiter and Saturn's gravity was able to basically send rocks in all directions, and it was these rocks that helped grow up Mars to be the planet we see today? In their models, what they were looking at is what would happen if it was the instantite chondrite meteorites. This is one type of non-metal asteroid. What if these were one of the primary building blocks of these early planets? It's thought that the ordinary chondrites are one of the first kinds of rocks that got used up during the period of heavy bombardment. Now, when I say heavy bombardment, what I'm talking about is a period when our moon became the cratered place that we see, Mars became much of the cratered place we see, and in fact, life probably wouldn't have been possible because there was just too much impacting going on. Now, what if the first rocks to get used up during this period were the ordinary chondrites, and then it was the instantite chondrites that came in later because of this resonance between Jupiter and Saturn? Well, after running their simulations, our team of scientists looked at, what do we think Mars is made of? In order to do this, we actually look at Mars meteorites. We haven't been able to go to Mars and bring back an actual sample yet. We're hoping to be able to do this in the coming decades. But for now, we're lucky that Mars sends samples our way. Whenever Mars gets hit by a particularly large asteroid, it will dig a hole into the surface and splash bits of bedrock, bits of surface material up into the atmosphere and in some cases, the rocks that get flung upwards from this impact are actually traveling faster than the escape velocity of Mars. These rocks that have been sent into outer space can then travel throughout our solar system, and some of them actually make it to our planet Earth. People who are out searching for meteorites all across our world are occasionally lucky enough to find one of these Mars meteorites. And in the hands of scientists, these Mars meteorites allow us to measure what is the surface of Mars made of. Now, it looks like right now about 68% is made up of these instantite chondrite meteorites, the ones that are thought to have been flung about when Jupiter and Saturn were in resonance, while 32% is made up of the ordinary chondrites. This is consistent with what would happen if we had the worlds built up in mass through this heavy bombardment period. But at this point, we don't have that many Martian meteorites, and the measurements have extraordinarily high error. This is only what's called a 2 sigma detection. So while this is tantalizing and leads to the inspiration of amazing artwork, at this point we aren't in a position to say, is this how Mars was formed, or is it not? Now, for those of you wondering, what exactly is this chondrite type of asteroid that I'm talking about? These are asteroids that are basically rocks. Meteorites come in many forms. There are those that are heavy metals. These are the ones that you most often are buying at, well, meteor shows, and they're the small ones that make it healthily to the surface of our planet. We also have meteorites that are made of regular carbonaceous materials like what we see, well, in regular everyday rocks. So when we start adding all of these fancy things to the word chondrite, it just means different kinds of rocks. So, put differently, it's looking more and more like Mars was built up by the collision of many rocks from space that come from two different chemical families. Now, not all of our news today is from within our solar system. Instead, we actually have what is kind of sort of an update on the Event Horizon Telescope. Some of you may have heard that several years ago, a variety of telescopes scattered across the planet Earth all joined forces to try and image the vicinity around our Milky Way galaxy's central supermassive black hole. We've all been waiting eagerly to see what kind of results, what kind of images are the product of these observations that have been taken place. And so far, we haven't gotten pictures. What we do have today is news that the ALMA telescope, the APAX detector down in ALMA, is joining in on the Event Horizon Telescope. And because of its position in Chile, it's going to allow us to start to understand different kinds of models of what that event horizon might look like. It's also going to increase the resolution on what the Event Horizon Telescope is able to see. With this particular telescope joining forces, it's thought that we'll be able to see details as close in as 3 times the event horizon of Sag A star, which is our fancy name for the supermassive black hole in the center of our galaxy. Now, unfortunately, this kind of a press release basically says, hey, we're one step closer to giving you information, but we're not giving you information yet. What I can tell you from this particular announcement is they see the event horizon in all of their images. They just haven't released them yet. So we're going to have to hang on a little bit longer, but at least we know the images are going to be even better than what we initially expected. Now, continuing to move out in what we observe and keeping to the theme of radio observations, we have new news on the neutron star binary astronomy front. Some of you may have heard back in August that LIGO, the long baseline interferometry system that has been detecting gravitational waves, thank you for the host over to ByteG. The LIGO system was able back in August to observe the merger of 2 neutron stars. Neutron stars are the end product of stars that are substantially larger than our sun, often as much as 2 solar masses. When these stars die, when they stop producing light down in their core, they collapse down under their own self-gravity. As they collapse down, they eventually reach this point where gravity's trying to squish them, and the protons, electrons are no longer able to support one another against this gravitational force. When this occurs, all of the protons and electrons collide together, smush together, and form neutrons. Thank you so much to ByteG for the bits. So finding these systems is cool because we know that when you have a neutron star merger, This is actually where most of the gold that you're wearing probably comes from. This is where, in fact, many of the rare heavy metals may originate. We're still working to determine this for certain, but it looks like, well, for gold at least, neutron star collisions are where it's at. Now, it's suspected that there should be as many as 100,000 pairs of neutron stars orbiting one another within our own Milky Way galaxy. So far, though, we've only been able to find 15 and now 16 of these pairs. Most of the pairs of neutron stars are found because one of these rotating objects is what's called a pulsar. A pulsar is what happens when you have a world that is rotating around a rotational pole and it has a magnetic pole that's at an angle to that rotational pole. And out the ends of this magnetic pole, we get flashes of light whenever the pole is pointed towards us. These stars can be extraordinarily fast rotating, in some cases having rotation rates measured in the milliseconds. And we found a lot of them in isolation. We found many of them in other kinds of binaries. But when we find these neutron-neutron star binaries, it's never because it's two pulsars. It's usually because we see the one pulsar with its misaligned rotational and magnetic pole. And as we measure the frequency at which that pulse is pointed towards us, we see it not repeating exactly the way we'd expect. And we're able to explain this asymmetry in its pulsation as the effect of it coming towards us and away from us as it orbits in a binary system. So far, most of the binary systems that we found that consist of two neutron stars have had very elliptical orbits. This means that the two stars orbit each other in not perfect circles, but rather in highly elliptical orbits. Now, recently, using old survey data, thank you, Uncle Bill, for the host over. Recently, using survey data from the Arecibo radio telescope down in Puerto Rico, a team of astronomers has been able to identify a 16th binary star made of two neutron stars. And this one is unlike anything we've seen in the past. These two stars are going around each other every 1.88 hours. These are stars more massive than the Sun that in diameter are probably about the size of Manhattan Island and are orbiting one another faster than our own planet is able to just rotate. Now, in studying this system, these two stars, or embers of stars, depending on how you want to look at it, are destined to someday merge together. The gravitational attraction is so strong between them that eventually radiation of this gravitational energy is going to shrink the orbits until we have a massive collision. This is the kind of collision that, just like the one we saw back in August, is going to produce gold and gravitational waves. Now, this probably isn't going to happen anytime soon, so we're not going to see that merger happen. But until then, this gives us a chance, our first chance, to study exactly what these systems look like in the lead up to these future collisions. Now, because it's Friday, it's kind of a slow news day. So that's all the news we have for today. But I'm going to stick around and answer any questions you may have. But only for a few minutes, because Matthew Richardson's waiting to take over the stream and get started with his Astro Office Hours. So welcome to the new people who've joined the feed today. Thank you for the shares. And if you're new and you like what you see, give us a follow. Follows are always free. We bring you the Daily Space every Monday through Friday at 1 p.m. Eastern, 6 p.m. London, and that's 10 a.m. Pacific. We also have many other shows going on here at the CosmoQuest Twitch channel. CosmoQuest is a project that works to put science in your brain. We invite you to tune in here, learn how we write our software to allow you to help scientists explore the moon, Mercury, Vesta, and other worlds, including our own planet Earth. And we also bring you data visualizations and other things that help you understand our universe a little bit better. So give us a follow if you like what you see, and remember, it's your subscriptions and bits that sustain our efforts. Now, I have to say, more than your bits, no, not more than your bits, but as much as your bits. I'd love it if all of you could take a few minutes at some point today or this holiday weekend, go to CosmoQuest.org and help us map out Mars and Mercury. We have a special need for science from those planets right now, and your help would mean a lot. So now to go and look through the questions. AstroWise is asking, why is it called a neutron star rather than just a binary star? So I was trying to be extra specific, AstroWise. There are people that just say binary neutron stars. There are people who say a neutron star binary. And by saying neutron star binary, I just want to make it completely clear this isn't a neutron star and a white dwarf. This isn't a neutron star and any other kind of star. So I'm just being extra specific. Both binary neutron star and neutron star binary are both completely legitimate ways of saying this. So Hanny is asking, since neutron stars are so small, has their mass been accounted for in the mass of the universe? Yes, and in fact, there was an amazing pair of research projects, Ogle and Macho, that looked for the gravitational lensing of background stars that took place due to nearby high mass stars, white dwarfs, neutron stars, black holes, specifically to get a limiting mass on just how much of our galaxy's mass is made up of these often invisible compact objects. It was thought for a while that maybe we can explain at least part of dark matter as just being compact objects that we haven't yet been able to detect. The Macho Project looked out at one of the Magellanic Clouds. The Ogle Project looked inwards towards the sphere of the inner nucleus of our galaxy, and by studying the brightness of background stars, they could tell if a foreground object that was high mass passed in front. When this happens, the gravity of that foreground object is able to take light that normally would go off and go anywhere but towards planet Earth and bend that light to come into our telescopes. When this happens, we call this a microlensing event. And by looking for the frequency of microlenses, we could determine how common these high mass objects are. And it turns out they're just not common enough to explain the dark matter that we see out there. So we have work to account for them. And it's cool science. It just isn't science that answers life, the universe, and everything. So I am being reminded that this is Tell Day, and at 42 views, this is kind of the perfect number of views for celebrating Tell Day. So happy Tell Day for everyone. I actually have a towel behind me. So from my towel to yours, remember, always carry a towel and always go out and look up. So this has been the Daily Space for Friday, May 25th. I'm about to hand this channel over to Matt Richardson, who's going to bring you our Astronomy Cast office hours. So don't go anywhere. He'll be picking up in just a moment. And one more time, the Daily Space is brought to you by CosmoQuest, where we work to put science in your brain. We are a production out of the Astronomical Society of the Pacific, a 501c3 nonprofit that is dedicated to increasing science literacy, especially in the field of astronomy. So thank you all for tuning in, and have a great morning, evening, afternoon, wherever in the world you may be. Thanks. Bye-bye.